Welcome to this video on the chemistry of dyes, a comprehensive study of ancient and modern colors. We will explore the classification, constitution, and applications of these fascinating compounds. We begin with the foundations of dyes, discussing what they are and the key requirements that make a substance effective as a color. A dye is a colored substance with an affinity for the substrate, typically dissolved in an aqueous solution. Unlike pigments, dyes penetrate the fiber, form chemical bonds, and provide long-lasting color. A good dye must satisfy three main requirements: color, affinity, and fastness. Color must be visually appealing and stable. Affinity is the ability to fix to the fiber. Fastness is resistance to light, washing, and heat. According to the Witt theory, dyes have two essential groups. Chromophores are responsible for the color, while oxychromes intensify the color and aid in binding to the fiber. Dyes must have adequate aqueous solubility to allow even distribution through textile fibers. Chemical stability is also crucial, ensuring dyes remain stable against environmental stresses like UV radiation and oxidation. Color fastness includes light fastness, which is resistance to fading in sunlight, wash fastness, or the ability to retain color after washing, and sublimation stability during high-temperature ironing or drying. Next, we will explore the historical perspective of dyes, tracing the journey from natural pigments to synthetic wonders. Before 1856, all dyes were natural, often expensive, dull, and difficult to apply. The transition to modern synthetic dyes, starting with Mauveine, introduced brilliant, cheap, and durable shades. Indigo, known since antiquity, is the king of dyes. Extracted from the Indigofera tinctoria plant, it is a vat dye, requiring reduction to become soluble. It is famously used for blue jeans. Alizarin, the madder red, was the first natural pigment synthesized in 1869. It is an anthraquinone derivative and a mordant dye, requiring a metal ion like aluminum or chromium to fix to the fiber. The synthetic revolution began in 1856, when William Henry Perkin accidentally created Mauveine while trying to synthesize quinine. This launched the mass production of affordable synthetic color. Now let us examine the classification of dyes by constitution, which categorizes them based on their fundamental chemical structure. Dyes are organized into a chemical hierarchy based on their core structure. This includes the largest group, azo dyes, along with anthraquinone, indigo, triphenylmethane, and phthalate dyes. Nitro dyes contain the NO2 group, such as picric acid, and typically provide yellow shades. Nitroso dyes contain the NO group, like fast green O, often used with iron or copper mordants. Azo dyes are the industry giant, making up 60 to 70% of commercial dyes. They are characterized by the azo group, connecting two aromatic rings. Examples include methyl orange and Congo red. Anthraquinone dyes are derived from anthracene, are very stable, and light fast, including alizarin. Phthalate dyes, like phenolphthalein, are derived from phthalic anhydride. Triphenylmethane dyes, like malachite green, are brilliant but have poor light fastness. Our final section covers the classification by application, categorizing dyes based on how they fix to the fabric. This includes methods like vat dyeing, reactive dyeing, and mordant dyeing. Primary application methods include acid dyes for wool and silk, basic dyes for acrylics, direct dyes for cotton, and vat dyes that are insoluble pigments requiring reoxidization. Reactive dyes form covalent bonds, while mordant dyes require a metal ion. Acid dyes have an acidic chemical nature and target protein fibers like wool and silk. Basic dyes have a basic nature and target fibers like acrylic and paper. Direct dyes are water-soluble and apply directly to cellulose fibers like cotton and linen. They are fixed by weak forces, resulting in poor wash fastness, but an easy application process. Reactive dyes are highly durable as they form strong covalent bonds with the fiber. They are known for their high fastness properties and are typically used on cellulose and protein fibers. Vat dyes are initially insoluble, requiring reduction in an alkaline solution to become soluble for application. The color is fixed by reoxidation back to the insoluble form within the fiber, providing excellent fastness. Dispersed dyes are non-ionic and have low solubility, typically applied as a dispersion. They are the primary choice for synthetic and hydrophobic fibers, such as polyester and acetate. Mordant dyes require a mordant, usually a metal ion, to create a stable bond with the fiber. These dyes are known for producing rich and deep colors with good light fastness. Beyond textiles, dyes have a vast range of applications. They are used in food coloring, printing inks, and in various medical and biological staining techniques. Dyes are also critical in advanced technology, including in lasers, solar cells, and photographic materials, demonstrating their importance beyond traditional coloration. The chemical industry faces challenges regarding dye effluent and environmental impact. Sustainable dyeing practices, like water recycling and using natural or less toxic synthetic dyes, are increasingly important. In summary, dyes are remarkable compounds defined by their chemical structure and affinity for a substrate. Their journey, from ancient natural extracts to modern synthetic molecules, continues to evolve. Thank you for joining this video on the chemistry of dyes. We hope you have a deeper appreciation for the science and history behind the colors that surround us.